Hello, BNG426 526 class. This is a little tutorial slash primer of how to approach homework 1, our ATP cost homework. I know several of you have had questions and concerns regarding how to start the thing, so I thought I'd put together a little video to hopefully help you out. However, what are we doing? So we're a cell. As a cell, growing and multiplying uses energy, costs ATP. ATP costs all over the place, as we talked about the first full week of class. We have the polymers of life, DNA, RNA, protein. We need them, and they cost ATP to make and ATP to maintain. And each of these things has separate costs, and there are separate costs also for making the building blocks as well as for polymerization. So if you are making DNA, there's separate costs for making nucleotides, and there's separate costs for putting all the nucleotides together in the form of DNA. Okay, so back to my however. Going forward here, please ask questions of me if you after you watch this video. I guess first I should say please watch this video, but please ask questions, especially if you still have confusion, if things still don't make sense. My email is here. You probably all already know it, which is good, but definitely please get in touch with me, and if you're still having problems by Friday, please let me know. Okay, so what exactly is going on here? Well, we're looking at Penicillium chrysogenum, a fungus. It's a mold fungus, same sort of thing. It's a well-established model system, so we know a lot about it. As is evidenced if you've read Chapter 2, there's a lot known about Penicillium chrysogenum. It grows on many types of substrates. It certainly loves to grow on nutrient agar. It can also grow in relatively harsh environments. You can see here this Penicillium is covering the skin of an orange. So it's probably not the most hospitable climate for a mold to grow, but Penicillium can do it. And what is Penicillium most known for? It produces penicillin, the antibiotic. Okay, so essentially we start at table 211 here in your book, in the Stephanopoulos et al. Book, where we look at two organisms, E. coli and Penicillium chrysogenum, and we see the contents per cell, or per gram cell dry weight, and the ATP cost to get those contents, again, per gram cell dry weight. So you have all the contents here in table 211. You will use those to calculate certain ATP values. And the question is, is it exactly that you're going to be doing? So you are being asked to calculate, or recalculate, I guess as the case may be, the ATP values for making and polymerizing protein, for making and polymerizing RNA, for making and polymerizing DNA, and for making the soluble pools of amino acids, as well as the nucleotides. And then you will calculate all the new ATP costs up with all these other ATP costs and get a revised total ATP cost. And so we're making some assumptions here, and I've outlined them on the homework sheet. So you'll notice that in table 2.8, aspartate and asparagine, as well as glutamate and glutamine, are lumped together. So what you will do is you will assume that you can just split them down the middle. Asparagine gets half of the ATP costs, as well as, that asparagine is half of the percentage listed in table 2.8, and aspartate is half the percentage listed in table 2.8. And then by figuring these things out, you can determine that they have half of the ATP costs of the lumped together thing. If that's still unclear, please come talk to me. Nucleotide percentages in the DNA are given on page 69, and the nucleotide percentages in RNA are given on page 70. Okay, so for your soluble pool, your grams per mole is going to be the average value for DNA and RNA nucleotides that is found on page 69. So you'll be using the information on page 69 and page 70 in your book quite a bit. We will not be calculating any ATP value for ash, nor will we be calculating any ATP value for metabolites, etc. Both of those are rather vague things, and it doesn't make a whole lot of sense to calculate an ATP value for them. Okay, so we look at table 2.8, which is a amino acid composition breakdown in mole percentage of cellular protein in the different species. Penicillium chrysogenum here is in the middle. And again, you'll notice that asparagine and aspartate, just like glutamate and glutamine, are lumped together, and both of the asparagine and aspartate make up about 9.6% of the amino acids in protein. So you can assume, and this is probably a little clearer than what I said before, you can assume that each amino acid, so asparagine and aspartate, make up 4.8% each of the total amino acids. So asparagine is 4.8% of the total amino acids in protein for Penicillium chrysogenum. Aspartate is 4.8% each of the amino acids in Penicillium chrysogenum. Same with glutamate and glutamine. Divide this 14.9% in half, and half of that is the percentage of glutamate, half is the percentage of glutamine. So that comes up to like 7.45% for glutamate and 7.45% for glutamine. Nucleotide percentages, here they are from page 70 for DNA and from page 69 for RNA. And you can see they're fairly consistent percentages for DNA, 25.5% for CMP and GMP, 24.5% for AMP and TMP. A little bit more varied for RNA for various reasons. But use those percentages when you are calculating your ATP costs. Okay, so how to get started. So you want to first calculate the ATP costs for making all these building blocks, for making amino acids, for making nucleotides. Then you want to calculate the ATP costs for polymerization. So for polymerization of protein, for polymerization of DNA, for polymerization of RNA. After that, or in the meantime, you can calculate the ATP costs for the soluble pools of metabolites. Do you want to calculate costs for polymerization here? The answer to that is no. You do not want to calculate ATP costs for polymerization of your soluble pools, because they're just that. They're pools of amino acids. They're pools of nucleotides. They're not polymerized into anything. Okay, and here, this is table 2.5. You can see a guide for the ATP synthesis costs per amino acid. Use these synthesis costs to calculate your overall synthesis cost. Here, this is table 2.6. You can see your ATP synthesis cost per nucleotide. And again, use these ATP synthesis costs. So we have all these tables and all this information. How do we make this relevant to us? So we have values for the amount of polymers and soluble building blocks in the cell, the total amounts. That was on figure 211. We have the values for the percentages of each building block. We have the ATP costs for making each building block. Now we have to put these things together, and the question is, how do we do that? Well, let's look at an example here. Say we take arginine synthesis. So arginine, from table 2.8, we can learn that it makes up 4.8% of the total protein. The ATP value for amino acid per arginine is 7 ATP to make arginine. So the amount of amino acid in Penicillium chrysogenum is about 0.196 millimole. And we should note, with this column here, we know the total gram of protein per gram of cells from table 211. You must convert this to moles or millimoles. And on page 69, you have a conversion factor. 110 grams per mole of protein-bound amino acid. You must use this in order to calculate the amount of moles of protein in the cell. And you can come up with your total amino acid, your total ATP per amino acid, which is 1.37 millimoles per millimole. millimoles of ATP per millimole of amino acid. So note on the amount of amino acid in Penicillium, you're using this 0.048, this 4.8%, multiplied by your millimoles of protein. That's how you arrive at this number right here. Okay? And you do similar things, again, based on the data in Table 2.5 and Table 2.8 to get all of the different amino acids. Okay, let's look at a nucleotide, AMP for RNA. So we have AMP. We get our percentage of the nucleotide, 25.6% for RNA. We get our nucleotide costs, our ATP cost per nucleotide from Table 2.6, 9 to make ATP. And the amount of nucleotide in Penicillium, and again, we are calculating this 0.256, 25.6%, times the millimoles of RNA, total RNA, which again, you have to calculate. You're calculating this using, again, information on page 69, 323 grams per mole of RNA-bound nucleotide. Okay? So you will end up with this number. You should end up with this number, 0.0079 millimoles. Your ATP costs per nucleotide, your ATP per nucleotide multiplied by the amount of nucleotide will give you 0.071 millimoles ATP per millimole of AMP that goes into RNA. Okay? Okay, arginine AMP. Now what do we do about polymerization costs? You know, it's well and good to calculate the ATP for making all these things. How do we put them together? Again, that information is on the information-packed pages 69 and 70. You've got these three equations here. Protein gives you 1 gram of protein plus a certain amount of ADP plus a certain amount of phosphate minus a certain amount of amino acid minus a certain amount of ATP. Well, this is essentially a mass balance, right? So for 1 gram of protein, you can assume that you're going to be using 39.1 moles or millimoles. I need to look at the pages 69 and 70 again, of ATP. So you will use this, the stoichiometry here, to determine how much polymerization costs you will have, or that you will incur to make the X amount of grams of protein, and you get the grams of protein from Table 211. However many grams of RNA, again, that comes from Table 211, but per gram of RNA made, it's a cost of 7.44 millimoles, I think, of ATP, but look that stuff up on pages 69 and 70. 1 gram of DNA, 11 ATP. Okay? So it's all there for you on pages 69 and 70. It's an important thing here. Okay, so again, we're looking at polymerization costs here. Let's take RNA. So we have ATP per gram of RNA, grams per mole, ATP per mole. So this is ATP per gram times gram per mole, right? And then ATP per millimole. And then we would calculate ATP per millimole times millimoles of RNA in Penicillium to get this number, 0.072. Okay, so the total macromolecule costs, both the building blocks and the polymerization costs, can just be added up. You have your total cost of ATP for making all of your building blocks. And then you have your ATP costs for making the polymers, for polymerizing the molecules. Just add them together. Add them together, and that's your answer. So if you're doing this for proteins, for example, you take the ATP cost for making all the amino acids plus the ATP cost for polymerizing those amino acids. And then that's your answer. And then your values would go where these red question marks are right now. Okay? Soluble pools, in comparison, your soluble pool calculation is a little bit simpler. You perform the same calculations per amino acid if you're talking about amino acids, or per nucleotide if you're talking about nucleotides, based on the amount per cell, which you can get from Table 211. Again, you must convert grams either to moles or millimoles, and you just have to make sure your units coincide with each other, agree with each other. And your conversion factors for nucleotides will say it's 316.5 grams per mole, Remember our initial assumption on the paper there. The amino acids is 110 grams per mole, just like with protein-bound amino acids. So for nucleotides, you just assume half of the soluble pool is DNTPs for DNA, and the other half would be NTPs for RNA. Okay, and then once you've finally done all that stuff, and it seems pretty complicated to get 5 answers, but for me it's worth it to understand, where all this stuff comes from. Then you answer question 2. Are your calculated values similar, the same, or different to the values in table 211? And these table 211 values are experimental values. Are your calculations in the same order of magnitude? Are they different? How different are they? This is going to tell you a little something about the way we have modeled the cell in this assignment. Have we made too many assumptions? Maybe we have. You'll find out. And you can just give a little opinion on what you think is going on when comparing the actual values with our calculated values. Okay, so if you have still questions, still comments, still concerns, please contact me. Ask me. I'm available, after class today. Today's Wednesday. I will be available definitely by email tomorrow, Thursday, and I will be on campus hopefully on Friday as well. So please come at me early and often with your questions, your concerns, and I'll help you get through it. And if you're still struggling by Friday, please, 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 please let me know about that. Thank you.